from nitrogen and hydrogen using iron as the catalyst, the production of methanol from carbon monoxide, and you can see that all these things involving products which are of very, very great importance in our everyday lives. They may be only a precursor of things that you and I see on a regular basis, but most of these things are generated in reactions which involve catalysts. So, the importance of catalysts are everywhere, and it is only appropriate that we look at this a little bit more carefully. Before we look at how it happens and what is the general principle of catalysis, let us just look at some of the kinds of materials which act as catalysts, and you can see in this list pretty much everything can act as a catalyst. Metals could be catalysts, metal oxides could be catalysts, metal sulfides could be catalysts, acids could be catalysts, and I have listed here what the type of material that we have got, what kind of reaction they catalyze, and what are the examples, prototypical examples of each of these. So, for dehydrogenation or for hydrogenation of the type that got Paul Sabatier the Nobel Prize for olefin hydrogenation involving metals here, semiconducting oxides of the type that are listed here could be used for any one of these 5 categories of reactions that you have got. Insulator oxides of the type that we have written out here, they could be used for dehydration and isomerization, and acids like phosphoric acid, sulfuric acid, and Lewis acids like silica and alumina could be used for polymerization, isomerization, cracking, and alkylation. So, you find that all kinds of materials, metals, oxides, metal sulfides, acids, and I have not listed here 2 very important classes of catalysts. One is zeolites and the other is enzymes, which also serves as catalysts. Enzymes, by the way, are naturally occurring catalysts that is there in our human body, for example. So, they catalyze a whole range of reactions. So, catalyst, as they say, is ubiquitous, it is there everywhere. So, it is only appropriate that we look at what happens in catalysis. And to keep going, one of the things that you will notice is that catalysts could be of any type, and here I have listed some of them. So, what we say here is catalysts could be in the same phase as the reactants. So, here I have just a variety. So, the catalyst is a liquid. So, the reaction itself, you imagine that I have a reaction A plus B going to C. That is a generic reaction, imagine that I am looking at, and this could happen either in the solid phase or in the liquid phase or in the gas phase. Reaction could happen in the solid, liquid or gas phase. It is possible that you have, if you have done any reaction, for example a titration experiment, the reaction is happening in the liquid phase, but there is no reason why reactions could not happen in the solid phase or in the gas phase. So, in principle reactions could happen in the solid, liquid or gas phase, and the catalyst also could be either a solid or a liquid or a gas, and that is what we have listed here. So, if the catalyst and the reactant is in the same phase, then we call this homogeneous catalysis. So, what are we saying? What we are saying is, if the reactant and the catalyst is in the same phase, then it is homogeneous catalysis. And here I have given 4 different, and there might be other possibilities. The catalyst is in the liquid phase, the reactant is also in the liquid phase, it is homogeneous, and here is an example, ester hydrolysis. So, this is ethyl acetate hydrolyzed by water in the presence of either acid or base. That is one example. The catalyst could be in the gas phase and the reactants are also in the gas phase, and this is an example. The oxidation of sulfur dioxide by oxygen in the gas phase in the presence of nitric oxide, which is also in the gas phase. So, this is the catalyst here. Here is the catalyst, here is the catalyst that I have underlined. The liquid phase catalyst, where the reactant could be both liquid and solid, and that is the hydrolysis of cellulose. So, this is the acid is the catalyst, it is present in the liquid phase. Water, which causes the hydrolysis, is in the liquid phase, and cellulose, another reactant, is in the solid state. A solid catalyst reacting with a solid and a gas. Here is an example: potassium chlorate decomposition. This is a solid, this is the reactant, and this is the example that is quoted in your book on catalysis. The decomposition of potassium chlorate does not happen very easily, but the moment you add manganese dioxide, this explosively undergoes a reaction. So, this is a solid and this is a solid, and the reactant is in the solid phase and the catalyst in the solid phase. So, here we have examples of homogeneous catalysis, and the reason we are interested more in heterogeneous catalysis is because of its applications in industry. So, now we move on and we look at some examples of heterogeneous catalysts, where reactants and catalysts are in different phases, and this we call as heterogeneous catalysts. Catalyst in the liquid phase, reactant in the gas phase. The polymerization of ethylene, ethylene is the reactant, acid is the liquid phase, phosphoric acid. Here is an example: solid catalyst, liquid reactant. Cyclohexene disproportionating, cyclohexene is a liquid, palladium is a solid, is a catalyst. Cyclohexene goes into benzene and cyclohexane, that is disproportionation for you. A solid catalyst with a gas phase reaction. Carbon monoxide is the reactant, zinc oxide is the catalyst. And a solid catalyst with reactant in both liquid and gas phase. The hydrogenation, which is in the gas phase, so hydrogen is one reactant, gas phase hydrogen, reacting with benzene, which is in the liquid phase in the presence of nickel as a catalyst, is an example of the last kind. So, I have now given you why we need to understand catalysis, and we have also discussed some examples of various kinds of homogeneous and heterogeneous catalysis. Now, what we need to do is to look at what all this means, and for this we will appeal to our knowledge from chemical kinetics. We already have seen, if you remember, recollect your discussion on chemical kinetics and something to do with the temperature dependence of rates. You plotted, if you looked, you plotted this both, whether it was in collision theory or temperature dependence of the rates, you plotted energy here and you plotted what is called the progress of the reaction. Or the reaction coordinate here. For any reaction, you plotted something which looked like this. So, whether it is E or H or G, it does not matter. Some kind of energy along this axis and a very strange variable called the progress of reaction. It's especially bad because it's called a reaction coordinate. It's easy to confuse this with some Cartesian coordinate, but it is not a single coordinate, mind you, it is a strange coordinate, something which tells you that the reaction goes from the reactant side to the product side, the reaction coordinate. And you plotted this. So, here you have the reactants and here you have the products. This separation in energy is the delta H or the delta G or the delta E of whatever this reaction that you are looking at. So, in this case, as I have drawn it, this reaction is exothermic, because the products are lower in energy than the reactants, and this is what is called the energy of activation for this reaction going from the reactant side to the product side. And this is what Arrhenius, we attribute this to Arrhenius, who wrote out this equation that the rate constant for this reaction is given by A e to the minus E A over R T. This is something that you must have come across in your discussion of chemical kinetics, and we will use this extensively in our discussion going forward. Okay. What does the Arrhenius theory says? This quantity here, the pre-exponential factor as it is called, is a measure of the number of collisions, is approximately a measure of the number of collisions that we have between two species that are undergoing the reaction. So, and you can compute the number of collisions by looking at kinetic theory of gases or something simple like that. So, this we know we have a measure of, and this quantity here essentially gives you the fraction of molecules, fraction of collisions with enough energy. So, what does this say? This tells you that you could have collision between molecules, lots of them. If I have two cars that come and collide, so the reactants look like cars, they come and collide. If the two molecules or cars coming together coming slowly, they will collide, will not have that much momentum, and so then they will have a collision. There are others which are coming fast and they collide. So, these have different energies because the kinetic energy of the molecules are different. And what we are saying is some molecules have the energy to overcome that barrier, and this is completely governed by kinetic theory. So, the fraction of molecules which have this barrier will go from the reactant side to the product side, and this is critical to understand, because if you want to understand catalysis, this is the key. So, I have, imagine a reaction between A and B, or let us imagine that is H2 plus O2 giving you half O2 giving you H2O. So, the reactant here, to give you a concrete example, is H2 plus half H2, and this is H2O. And if I looked at this reaction H2O, the delta G is very largely negative, something like minus 250 or so, approximately minus 250 kilojoules per mole. That is what we have. But you can keep H2 and O2 mixed in a container without a reaction ever happening between these two. You keep these two mixed, although the Gibbs energy is negative, you can stay there forever. But the moment you add some metal like iron filings or some other metal, these two react explosively to give you water. So, this is a very, very subtle thing. So, the Gibbs energy is negative. So, it is thermodynamically feasible reaction, but the reaction does not happen at all until I had some iron filings or some other metal. So, what is it that the catalyst, in this case iron filings or some metal that is added, what does it do to make this reaction go from here to here? And the way it does this, the catalyst, what it does is to give an alternative path to go from the reactants to the products. So, here is one well, this well, so this is a catalyzed reaction. This picture looks a little bit different from the picture that is there in the book, but I will explain that in a moment. So, H2 and O2 in the presence of a catalyst will get adsorbed on the surface of the catalyst, as a result of which the energy goes down. That is this point here. So, this point corresponds to hydrogen and oxygen bound to the catalyst surface, which is not there in the absence of a catalyst. So, this is this dip. This hump corresponds to the activation barrier for the adsorption process. And look at this, this barrier is much smaller than this barrier, and that is the key. So, you get into this, now I have an activation barrier to go from this, a reaction happens. So, I have hydrogen which is adsorbed to the surface, oxygen that is adsorbed to the surface, and this point, they undergo a reaction, and now I get water. This point here corresponds to water which is adsorbed to the surface. So, that is why this profile looks a little bit different from the one that is there in the book. The one that is there in the book just shows you like this. So, this is adsorbed hydrogen and oxygen, this is adsorbed water, and then it goes over this hill and gives you water. So, note critically, and this is what the definition of the IUPAC has, the Gibbs energy change in going from here to here is exactly the same for the blue profile as it is for the green profile. So, for the catalyzed reaction as well as for the uncatalyzed reaction, the Gibbs energy change is the same, which means that the equilibrium constant, product over reactants, is the same no matter whether you put a catalyst or you do not have a catalyst, which means that the forward rate is affected exactly the same way as the reverse rate. So, the equilibrium constant is completely unaffected. That is why it says that it increases the rate of the reaction without changing the Gibbs energy change of the reaction. The Gibbs energy change here is unaffected by the presence of a catalyst, whereas the rate of the reaction is. But there is something that you have to be worried about in this picture. This picture connects reactants to products. This does not mean that the catalyzed reaction goes through the same path as the uncatalyzed reaction. And this is like saying, I will try and give you an analogy. Imagine that I have to go from point A to point B. There is a straight path which goes here, and imagine that I have at this point a red light here. That is my red light, and this red light, because of the traffic, is hugely clogged. So, imagine that I have a huge traffic jam here. So, molecules which come from here, cars that come from here, because of this traffic light which takes long to change, and because of the numbers of things here, getting to B is difficult as a result of this traffic light. The smart drivers avoid this traffic light and take another path which does not have any lights. So, now if you are a molecule, rather than go through this straight path, you run from A to B, but it looks like the distance you are traveling is more, but because you have short circuited this red light here, you reach to B faster, and that is exactly what is happening here. Here you have an uncatalyzed reaction, and this red light corresponds to the huge energy of activation that you've got for the uncatalyzed reaction, whereas here, because you have no red light, this happens to be the catalyzed reaction. So that's the analogy between something that you encounter on a regular basis. Don't push the analogy too far, but it gives you a way of understanding how a catalytic reaction works. Okay. The other thing that we look at is, if you plotted, what we are saying is the EA of uncatalyzed reaction is much greater than the EA of the catalyzed reaction. So, if you plotted ln k versus 1 over T, we know from our discussion in chemical kinetics that it looks like this. So, imagine this is the uncatalyzed reaction. And imagine I am looking at a reaction where I am using a heterogeneous catalyst. This point here corresponds to ln A, which we said is a representation of the number of collisions. So, we have this for the uncatalyzed reaction, and for the catalyzed reaction we are saying that the energy is smaller. So, if you looked at this, this happens to go like this, and this is the catalyzed reaction. Why do I represent this as smaller? Because now the two species are adsorbed on the surface, and once they are adsorbed on the surface, the number of collisions that you have is going to be lower than if you have in the gas phase. Imagine that you have lot of molecules in the gas phase, some of which gets adsorbed, and once you are adsorbed, the number of collisions that you have is going to be significantly smaller than the number of collisions here. So, there are two counteracting things. The heterogeneously catalyzed reaction has a smaller number of collisions, but it also has a smaller EA. So, this EA cat, and this is again a little bit counterintuitive. The slope is lower for the catalyzed reaction, the slope is higher for the uncatalyzed reaction, right. ln k is equal to ln A minus EA over RT, and the catalyzed reaction has a larger slope, which is here. So, the number of collisions is fewer in the catalyzed reaction, but EA is also smaller. So, if you have to have the catalyzed reaction actually work faster than the uncatalyzed reaction, you have to compensate for the decrease in the number of collisions by seeing a larger decrease in the EA. And here are two examples of, I am giving you some examples of what kind of EAs that we are seeing here. So, here are some examples. Here is the reaction of hydrogen iodide to give you H2 and I2. In the absence of a catalyst, the activation energy is 185 kilojoules per mole. In the presence of gold, it has gone down by about 80 kilojoules per mole, and for platinum it is even further down. So, the number of collisions that you had is compensated for by this change in the activation energy. And here are two more examples. In both cases, we will find that when you have no catalyst, the energy of activation is higher than when you have a catalyst. With that, we will close for the day. Thank you.